but to communicate, hey, when I get to this step, this is how I'm thinking about it. Can you show me how you got to your answer? And then, you can figure out from there where each other is at. But yeah, like I got some submissions where part two didn't match part three or part two didn't match part four. And when we're turning in group work, we all want it to agree. We don't want it to contradict itself, right? That's all. Otherwise, overall, it was great work. Everyone did a really good job. And I think we're on the right track for this exam one.
So the other thing to think about, so on Friday, remember, we've moved our test from Friday to next Monday. Reminder, okay, a week from today, we will have our first test. There does not seem to be a class in here before us. So Ty and I will be here, or at the very least, Ty will be here at 8:30. And you can start your test at 8:30. And then that way you've got some extra time. If you want to come and just hang out and study, that's also fine. We'll make sure everybody's quiet and those things. Okay. But on Friday, we're going to play a review game. We're going to play Jeopardy. Okay. You will be on a team with the people in your group, which is going to be a nightmare for Ty and I because there's going to be a lot of groups.
Maybe we can group them by the twos, like put two groups together.
Maybe we'll do that. Ty and I will squish two groups together because there's a lot of y'all.
Yeah, and I don't think
So rather than there being 25 groups, there'll be like 12.
Yeah.
Okay. We will play Jeopardy. Whoever wins at Jeopardy gets a bonus point on the test. Okay. You cannot use your notes or anything else on Jeopardy, but if you want to start studying or doing things now to prepare yourself, or you want to try to explain things to your group members in an effort to get ready, then we'll see how that goes. Okay, but that's going to be our plan. We'll finish, I think, control of force production today. We'll do sensory motor integration stuff on Wednesday and probably have a little bit of time for some questions. And then we'll do the Jeopardy review on Friday. Okay. All right. Anybody else have anything you just desperately need to get off your chest in front of the entire room? No. Nobody. Going once, going twice. Anybody have really exciting Valentine's Day plans? So everybody, Valentine's Day is Saturday, right? We are aware of this. This is a reminder for everybody. Okay. Maybe a little late to make a reservation, but if you haven't, think about it. Okay. You still order some flowers. You can still go to Walmart and buy some candy, whatever it needs to be. Make something very thoughtful. Ellis is making this giant box to take to her class that they put their nondescript, not addressed to anybody Valentine's into on all of this. Usually we do a shoebox. We had something get delivered in a box that's like this, and she was like, I want the giant fucking box. So we're crafting this huge box. Which meant I had to put construction paper all on the outside. Anyway, there we go. Helicopter parenting at its best. All right. Before we do force production, part of the thing that we get from doing some of the assignments and things was Ty wanted me to go over for everybody the idea of a graded potential. Okay. A graded potential. There was a little bit of confusion on this potentially on the group assignments. Okay. Anyone think you know what a graded potential is and want to share? Right.
When excitatory postsynaptic potentials start to build up the cell body until it eventually reaches threshold. Potential starts. So it's like the little signals before the actual action.
Okay, well, perfect. Okay, excitatory, postsynaptic, all those are lovely neuroscience terms that we don't actually have to know. But the idea behind the graded potential, okay, is this is the small change in membrane potential. That is the initial sort of thing that we're picking up in the cell body. So if we have an alpha motor neuron here, it has a resting membrane potential of -70. Okay. As you begin to send signals from the motor cortex down the spinal cord, okay, the spinal cord is just a collection of nerve cells. It's a collection of neurons. In this instance, I'm representing these neurons around the alpha motor neuron here and here as things that we call interneurons. They exist between the other neurons, okay? These interneurons are going to depolarize, and they're going to send a signal to the alpha motor neuron, as I'm showing here, that is picked up by the dendrites, okay? It's picked up by the dendrites. As this small signal gets picked up, our minus 70 starts to take a sort of positive turn, okay? This is that postsynaptic excitatory signal that we are getting. It's going to start to come up this way. If, let's just say, I get one little signal from an interneuron, it pushes me a little bit positive, and then nothing else happens, it goes back down. I do not get an action potential, okay? This right here is a graded potential, okay? This little blip is a graded potential. In order to get a motor neuron, or any neuron for that matter, these interneurons even, to fire, we have to get multiple graded potentials that add together, okay? They add together. So I get one, then I get a second one, then I get a third one, and now I've reached threshold. Once I reach threshold, boom, it's going to go the rest of the way, okay? And that's the idea of a graded potential. It's this sort of, there's one that got me to here, and a second one that got me to there, and a third one that got me there. And I don't know, sometimes it could be, honestly, I'd have to Google it. It might be 10 or 20 or 100 graded potentials that get us there. You get a lot of signals in there, but that's what the idea of a graded potential is, okay? It's a brief positive sort of electrical signal picked up by the dendrites that moves threshold in the motor neuron towards threshold, moves it up positive, but all by itself is likely not going to be large enough to get us to threshold and depolarize. That's a graded potential. Okay. So you usually are going to get your signal, you get a graded potential, you get a second and a third graded potential. Now we get to threshold and we get an action potential in the motor neuron. Okay. Does that make sense? Oh, y'all are going to be doing squats today. It's Monday. We're a little sleepy. We're going to squat anyway, but there we go. Hope you all wore your stretchy pants. Okay. All right. That's the idea behind that. There we go. Okay. Everybody stand up. I told you we were going to squat. I was not lying. Okay. Are we all ready? Okay. We're standing. You guys know how to do a squat correctly, like not up in our toes, not way back in our heels or anything. We're gonna keep our back in the right position. Okay. Here's what we're gonna do. We're gonna do a squat, and while you're squatting, I want you to think about, okay, where in that squat you are the strongest. Okay. So squat with me. And we're my stretchy jeans today, which is like a great invention for dudes. I'm just going to tell you all that. Like I got dress pants and jeans that are stretchy. I don't know where that's been for the first 35 years of my life on those things. All right. Start here. Think about how strong you are right here. How much weight could you hold here? Okay. Now, go down with me. Okay. Down, 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 all the way. Don't sit. Down. Okay. Now we're going to go up. So slowly slowly work our way up, Think about where in here am I the strongest? Okay. Who wants to give me an answer? If you've got a weight and you can unrack the weight and hold it here, are you pretty strong right here? I mean, it doesn't really matter. You're cheating. You've locked out everything. Okay. But as I go down, where do you get stuck? The bottom, someone says, like here. If I can get past, right, like here, can I get the rest of the way up? Okay. Why? Why is that the case? Everybody squat and see if you can get stuck. Should tell you pick your neighbor up on your back or something. Every morning, Ellis makes me give her a piggyback ride from our car into school. All right. At the very bottom, are you thinking about as you come up? Where, as I'm coming up, is there a point like if I can get to here, I'm good, right? I can make it all the rest of the way up if I can get to there. Okay. My question for you guys is why? Why is that the case? Okay. Y'all sit, and I'm gonna get an actual answer. Who thinks you know? Okay, Nick. Okay, great question. Nick says, is it because the filaments overlap more the higher you get? Which would in some ways correspond to what I have on the screen right now. Okay, so we're going to walk through this and see if it matches with what we just did, and then we'll discuss a little bit. Okay, so but you all at least have the idea that I have the same amount of muscle no matter where I am through that range of motion, right? My muscle size doesn't change. My pennation isn't really changing. In theory, my ability to recruit motor units it's not always the same, but we'll say it's roughly similar. Here. And then let's say that my firing rate to those motor neurons is roughly the same. I have the same capacity to do that no matter where I am. And yet, all of those things being the same, I can lift a different amount of weight. I'm differentially strong at different points in that range of motion, right? We all at least sort of stipulate I know we don't have a lot of lawyers in the room. We'll at least stipulate that that's a true statement. Okay. So we got to figure out why. This is a real thing that matters when we live. Okay. So what I have drawn here, what I'm showing you guys data from the 1960s on here, is something called the sarcomere. I know I have written muscle length and force production, but this right here is what's called the sarcomere length tension relationship. Okay. Sarcomere length tension relationship. And so if you graph out force production based upon the spacing of the sarcomere, okay, if a sarcomere has a certain amount of overlap, if we stretch that sarcomere way out, it looks like this. Or if we shorten it way down and it looks like this, we go here. Very short sarcomeres, not much force. It gets a little bit longer, we get more force. There's some kind of optimal overlap or stretching in the sarcomere. And then as it gets stretched out, as it gets pulled out, force goes down. Okay. What this tells us is that at different levels of stretch or different levels of shortening, sarcomeres generate a different amount of force. And this should be very obvious because where does the force come from? We're going to hit this. It'll be like the first question on the band test. Force comes from what structure? Someone said myosin. Okay, good. But you can't. I have myosin in my arm and it's not generating force right now. What does that myosin have to do? Cross bridge. Force comes from cross bridges. Okay. So look at this when I've taken a sarcomere and they do this. They dissect out a sarcomere, they stretch it way out. And I get almost no force production because look, here's myosin, there's actin, there's no overlap. Because they're not overlapping, the myosin can't grab onto the actin and you cannot form a cross bridge. No cross bridges, no force. Okay? No cross bridge, no force. As we shorten it down and we move this way, as we shorten it down, we start to get some overlap where I can have myosin grab onto actin, I can make cross bridges, and I get some force. Okay? I get some force. Now, this weird thing that happens when it gets super duper duper short is the actins actually slide all the way past each other, and we begin to lose some capacity to have overlap. We lose some actin that myosin could bind onto. You get a thing called mechanical interference, and we get almost no force there. Okay? So, think about this. Think about my quads. Okay? Watch the Olympics. Watch the freaking skiers. You want to see people that have amazing function in their quads. Good Lord. Okay? Watch them ski the slalom or the downhill. Y'all seen the downhill stuff? Those dudes are going like 95 miles an hour and then like doing jumps and shit. No way. I'm sorry. Right? You're gonna crash and then you're gonna be like Lindsey Vonn and you will break a bone and all of that. Like those people they're just amazingly brave in all of that. Because I'm just like, I'm good. I'm out. No way. Okay. Quads. Are my quads lengthened, shortened, or somewhere in the middle right here? Make Cindy proud. Come on. Lengthened. We sure? Sure they're lengthened? Shortened. As I go down, what's happening to my quads? As I get way down here, I'm not very flexible. Stretching is terrible. As I get way down here, are they super lengthened?
Yes.
Okay. Then back up in here, they're somewhere in the middle. Shortened, somewhere in the middle, lengthened. Shortened, somewhere in the middle, lengthened. Where was I weakest? Shortened? Maybe.
At the bottom.
The bottom. And what is happening to my muscle at the bottom? Right.
There's very little tension.
I'm sorry?
Well, there's very little overlaps.
There's very little overlap. So I'm right, somewhat strong, probably a little stronger, weaker, 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 weaker as I go down. Does that correspond to this? Alex is like, yeah, I think a trick is coming on all of this. Okay. So this is what happens in your sarcomeres. Okay. This is what happens in the sarcomeres. What I'm going to tell you guys is that that looks like what happens as we move through a range of motion. We can do it in the bicep too, lengthened, middle, shortened, weaker, stronger, maybe a little bit weaker again. Okay. It looks like that. But what happens in your sarcomeres in real life is they rarely leave right there. As I move through a range of motion, my muscle is shortened. My sarcomeres are not that short. As I go down, my muscle lengthens. My sarcomeres are not that lengthened. Okay. It looks like this. This is a real physiological phenomenon. But this, what happens at the sarcomere level, does not have a huge outsized influence on force production in your muscles in real life. Okay. Mostly because our joints limit our range of motion. You can't get that stretch. Okay. Like you can't, maybe some of y'all can hyperextend your elbow. I can't. But because of that, you can't ever really stretch your muscle as much as it might look like this. Okay. So this is sarcomere. You need to know that this is a real thing that could happen, even though it rarely happens. So now you should be saying, well, what the hell, Dr. Blythe? We all agreed, you stipulated, and I tricked you, that I am stronger, weaker as I go down. If it's not this, what is it? Where does it come from? You, sir, you are Joey. Okay, we gotta get you a name tag, Joey, so I can learn names. We got a couple of other folks that don't have that don't have name tags, so I can go. Joey, what were you gonna say?
Have to do with like biomechanics more and like mechanical advantage.
It absolutely has to do with biomechanics and mechanical advantage. That's right. It's all about biomechanics. Okay. But do you know what it is about the biomechanics and mechanical advantage? Do you know the thing that matters off the top of your head?
The length of the lever.
The length of the lever. Good. Right? I have very short levers. Which actually is good for me for squatting and for curling and for bench pressing, especially. The length of the lever. Where is the lever in my knee? You guys know? Where's the lever? Most of our joints are what we call second class levers, right? Where the insertion is on is on one side, where the load tends to be on one end, and then the insertion is between the load and that, rather than it's actually not particularly advantageous. We have a bunch of second class levers, which means we leave a lot of force production on the table by doing that. But in my knee, where is the lever? If I do knee extension, if you guys can see me, okay, if I do knee extension, quad, right? Quad pulls on the patella tendon. Where does the patella tendon attach? Where does it insert? Down here on my tibia, right? I gotta be impressed with my anatomy. Right? Patella tendon, tibia. So what's happening actually when your quads do something is they are pulling your leg up in this way, just like if I was to grab on and pull like that. So the lever, those of you that have had physics or something, or if you've had biomechanics, how do we measure the lever? Where would we even begin to measure the lever? Who wants to guess? No, please go ahead. From knee to hip? So purely, if we're doing a squat, that matters. Like an actual squat, that matters. Me sitting here, presuming that I'm doing this, right? That distance isn't going to matter because I'm really not using my hip flexors if I'm doing an isolated knee extension like this. But you're correct. For you do a squat, you're getting knee extension, you're getting hip extension, and some things. So it's more complicated. But just at the knee, let's just say. Right.
You take the torque at the knee.
We would take the torque at the knee, right? But how do I calculate a torque? I got to know what my lever is in order to calculate that. So
The distance between knee joints for the muscle.
you're so close. We're so close. Sorry, I got to look around with our Riley with 2 exclamation points. You're so close. The distance from the knee to where the force gets applied. Okay, so we calculate what's called a moment arm or a lever arm. It's the distance from here in the knee down to where the insertion is. Okay, down to where the insertion is. So when we move, most of our movements are what we call angular from a physics standpoint or a biomechanics standpoint. They're angular. We have rotation about the joint. Okay, so that means that we must consider not only the force that a muscle produces, but also the moment arm, which lets us calculate something called torque. Torque is the angular analog to force. So my quad generates a force, it pulls on the patella tendon. Where it inserts on the tibia, we have to know that distance. It's like being on a seesaw or something at the playground. Okay? The farther down my leg, right, the farther the distance from my knee to the insertion, the bigger the moment arm, and therefore the more of the force from my leg that's going to get applied down here, right? If you guys had to think about the lever arm on all of that, the longer the lever arm, the more force gets transferred, right? If you're going to pry something up, you want the bar to be long, right? In some ways, if it's really short, you don't have much mechanical advantage. So, a weird thing happens, okay? I am here, and there's a distance from the knee to the insertion. Okay, it is a distance. Let's just say it's 6 centimeters or something. Okay. As I start to go down, the biomechanics move in my knee, and that distance actually increases a little bit. And then as I get way down here at the bottom, as it folds back under, it actually becomes a little bit shorter again. And so what we know in human movements at joints is the moment arm changes in real time based upon the angle of the joint. And for a lot of our joints at very, very sort of extended and at very, very flexed points in the range in motion, the moment arm tends to be a little smaller. And somewhere in between there, the moment arm tends to be biggest. So what that means is my ability to transfer the force of my quads to the tibia and therefore to the ground to overcome gravity and lift this weight changes if I'm here versus all the way down, even though my quads are the same size, my motor unit recruitment is the same, my firing rate is the same. The force from the quads is identical, but its application changes. Okay. When you do a curl, most of you, if you've done a curl, which I know on Friday, a lot of y'all said you had, right? If you can overcome about right here in the curl, you can do the top part. You get stuck at the bottom. You get stuck at extension, right? So if I get past here, my moment arm gets a little bit bigger and I can apply a little bit more force, okay? When we measure strength in sort of these angular movements, right? How much can you curl? How much can you squat? How much can you bench? You're only as strong as the weakest point in your range of motion. You can only lift up and squat up, right? The amount that the sort of at your weakest point. I can squat 200 pounds, let's say. I can't squat 201. I can squat 201 in the middle. You've all seen the people, they go do their squats, do like little quarter squats, think they're doing real good. They didn't have a football coach for that. He was like, no, farther, get down, let's go. My dad thought power cleans were the cure to everything. Okay, I am not explosive at all, but I have chef's kiss power clean form. Let me just tell you on all of those things. I would smoke some things at CrossFit. The CrossFit would kill me otherwise, but my clean form would be great. Okay, you're only as strong as the weakest point in your range of motion. And so we can determine all of this in real time, okay, with what I call an in vivo. In vivo means in an intact animal. We are animals. I don't want to say that out loud. We are at our most basic, right? We are mammals like everything. The in vivo in an intact human length tension relationship is actually should be characterized as a torque range of motion relationship, a torque joint angle relationship. Okay. And what I have here are some data from a guy whose name is Rick Lieber. These are from the late 80s, but Rick is a muscle physiologist, but he was at the University of San Diego and he was partnered with an orthopedic surgeon, and people would come in and have they did a lot of stuff in the hands and the fingers. They'd come in, have surgery. And while people were knocked out, they would tug on the tendons and stuff for their fingers and measure force production while they would get permission to do it, but they would measure stuff. And so what you can see here is some data of theirs with knee angle, okay, sarcomere length, effective lever arm or moment arm, and then actual force production. And so you will see that the sarcomere length changes and it has a little bit of an influence on things, but most of what we see here with actual application of force is based upon the effective moment arm or the effective lever arm across the knee. Okay. And so what tends to happen is just very, very simply, when the moment arm tends to be the largest, which in most people is in the middle of a range of motion, we get more torque. When the moment arm is small, which tends to happen near full extension and near full flexion, we get less force. And that's why you get stuck at very predictable points in your range of motion. Very often at highly extended sort of positions, depending upon what your muscle is. Okay. So there is some effect of sarcomere overlap, but generally in intact animals, the sarcomere overlap is mostly pretty optimal most of the time. Okay. It's mostly pretty optimal. It's all about momentum. Now, some of you may have a friend who is the same size as you or smaller than you, and yet, as we talked about, you both train a whole bunch, and yet they're just stronger, right? It may be that biomechanically they have sort of more optimal or longer lever arms on their insertions across their joints, right? You can both recruit to the same extent, you both have similar sized muscles, but their ability to actually generate torque and apply that is very different. Okay. I get an advantage when I bench press because my arms are short. Okay. I don't have to move very far. Right. That's better. But I was a baseball player in college. I can't throw the ball with the same velocity as someone else because my arm is short. Right. The sort of lever arm from shoulder to application of force out here is shorter. Someone that has longer arms can apply much more force in that one, or the same force gets turned into more torque because they have a longer lever in that way. Okay. And so this is how this other complicating factor plays some role in our ability to apply force. It's not just about muscle size. It's not solely about all of that. It's also about the task. And does that task make you move through a certain range of motion? Okay. Well, you can squat more if you don't have to go down as far. And we can argue, should we not? Does it matter to get to that long length? I don't really know. Okay. That's a whole kind of separate conversation. But that's the idea behind all of that. Okay. All right. The last sort of thing that I want us to cover as we talk about what matters. Everybody stand up again. Stand up again. Okay. It's going to be great next year because we're going to have a lab with class. Okay. Sorry, y'all are the last group of the second to last group that's ever going to have to take senior capstone. So we're changing. It's going to be an option. You're going to have a class in research method, but in the fall, we're changing our undergraduate program. There's going to be a 1 hour lab, kind of like with chemistry and biology, that goes with this and with testing prescription. And capstone becomes an elective class on this. So sorry, everyone's like, damn it. Anyway, all right. Everybody do this. Give yourself just a little tiny bit of space. Okay. I want you to do a curl. Do a curl for me. Do a curl. Do it really slow. Slow curl. Okay. Nice and slow. Okay. Now, curl as fast as you can. As fast as you can. Right? Caden is just over here sandbagging us on this. That's all you got?
I don't want to hit myself in the face.
Sure. Okay.
I'm being careful.
Well played. Well played. All right. Now, pick up your backpack. If you are able, curl your backpack. Okay. Now, curl your backpack as fast as you can. Okay, stop. All right, this will be fun. Olivia, could you curl your backpack as fast as just your arm? Could you curl your backpack as fast as you could curl just your arm? You would say yes. Oh, okay. She's showed me. Who's got a really heavy backpack? Okay, Riley, your backpack's heavy. You were going slow?
Yeah.
Okay. Anybody else have that experience? We should all be like, Olivia's just very well trained. We're gonna say positive things, all right? So not that she doesn't have any books in her backpack or anything else. Y'all don't have to have books in class. Okay. How many of you thought that was pretty standard? You thought it was a little slower with the backpack than it was just with your arm. Okay. Some of you all are like, nah, I'm good. I'm not gonna say anything. Okay, sit down. The last thing that we must consider when we talk about how much force we can apply when we do a particular task is velocity. Okay, is velocity. And this presents itself in two ways. Okay, in two ways. We can have our ability to lift some external load, 5 pounds, 10 pounds, 20 pounds, whatever it is. And we see how fast what's the fastest you can move that. Okay. Or we can basically come to the lab, let Ty test you. We put you in a machine that moves you at a given velocity and you try to kick or pull against it as hard as you can. And at that velocity, we see what the max force you can produce. We see the same thing here. Okay. Velocity matters. In general, during a concentric contraction, please write this down. During a concentric contraction, to go fast or have a high velocity, force production is low. Okay? Force production is low. Which was why most of us have an experience like Riley did, where your arm doesn't weigh that much. It can go pretty darn fast. We give you a heavy thing to curl and it goes much, much slower. If you go to the gym today, it's Monday. We all know what the bros are doing today, right? Chest day. Watch and see if any of them are lifting very heavy and watch how fast they can move the bar. It's probably not very fast, right? To get a lot of force, you got to go slow. It's like really, really slow. Okay. Under concentric contractions, to get high velocity, force is low. So it looks something like, let me show you guys what this half of the thing looks like. It looks like what's going on over here. This is a graph that's called the force velocity relationship. We're going to focus on the right side of the graph to start with. Okay. This is a concentric contraction. Okay. As we move from this midpoint to the right, we're going faster. It's a faster and faster and faster concentric contraction. Goes from slow, 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 slow to a little faster, to faster, to as fast as I can go. Okay. That's what's happening here. As velocity increases, force goes down. Okay. Force goes down. That's the way the relationship works. Okay. I'll explain to you isometric, then we'll try to talk about why that's the case. Okay. An isometric contraction on this graph happens right here on this midpoint line, right here. Okay. An isometric contraction has zero velocity. Zero velocity. The muscle does not change length. Nothing moves. There's no velocity. That's why it occurs right on this line between shortening velocity or lengthening velocity. It is there. As you look at this, an isometric contraction, if done correctly, you should be able to generate more force isometrically than you can concentrically. Okay? You can hold more weight right here in the middle of the curl than you can actually pick up and do a full range of motion. Okay? Isometric force should be higher. Okay. We're going to come back to where we were at the start of class. Where does force come from? Cross bridges. Okay. So, if as I go faster, force falls, what am I getting less of? Cross bridges. Okay. And that's correct. As I go fast, I get fewer cross bridges. We can accept that. The real question, though, is why? Why are there fewer cross bridges when I'm going fast? Anybody want to guess? Anybody want to read off the slide? Brian, go for it.
Cross bridges have to detach faster and faster.
Cross bridges have to detach. Okay. In order to shorten a muscle, think about like your muscle is playing tug of war with the tendon. Okay. We've grabbed on. And if I want to pull slow, I can have, imagine that I'm like an octopus and I got like 8 hands. Okay. Or we're all on here pulling. To pull fast, I got to let go. I got to pull and I got to let go so I can reach back down. Or if I would let go with this hand and reach back down like this, right? When I let go, guess what happens? That arm or that cross bridge can no longer apply force. Okay? So if I'm pulling really fast at any instant in time, if there were 100 of us pulling together, if we're pulling really fast versus pulling really slow, more of us are going to have a hand off of the rope trying to reach forward than we would if we were going really, really slowly. And that's the idea of what happens in your muscle during a concentric contraction. In order to shorten, we must run through the cross bridge cycle thousands and thousands of times. Okay? And if it goes fast, then more myosin at any instant in time are going to be detached. So we have fewer cross bridges at any instant in time. And that's at the same size of your muscle, at the same joint angle, at the same motor unit recruitment. It's just that physically, at any instant in time, going fast, there are fewer cross bridges. And that's why when you go fast, you get less force. Okay? That's why you get less force. Okay. So if isometric gets us more force, I'm not changing length. I'm just holding on to the rope. And so if we're stuck and we're holding on to the rope, what do I not do when I do an isometric contraction? I'm just holding on. What's not happening? Somebody said it. Just say it again a little loud. I'm holding on. What's not happening? It's not moving, that's right. But because it's not moving, the length isn't changing, yes. But what are my hands always doing if it's not changing length, if I'm just here? I'm never letting go. Okay? When we do isometric contractions, the rate of cross bridge cycling is very, very low. There's a little bit, but it's very, very low. Because it's very low, I get sort of max amount of cross bridges. So I get more force because there's no velocity. I don't have to break them and let go and reach on down on the rope. Okay? Also, when do we use the energy during a contraction? To relax. Very good. Hey, okay. Good, Ken. To relax. So if I go really fast, I'm breaking the cross bridges and relaxing a bunch. So what happens to energy use? It goes way up. When I do an isometric, and I don't have to relax, I don't have to break the cross bridges, I don't use much energy. So again, I can generate more force and I can hold it for a much, much longer period of time because it's not very metabolically taxed. Whereas when you go really, really fast, right? I am sprinting. Very, very high energy. All because of the cross bridge mechanics, because of the cross bridge cycle, because of the cross bridge turn. Okay? And this is why we harp on the signaling pathway and we harp on actin and myosin and cross bridges until we're blue in the face. Because your ability to move and generate force and how much energy that costs us and why it is different under different scenarios all comes back to actin and myosin. It all comes back to the cross bridges. Okay? Now, in our last 5 minutes, what happens on the left side, on the eccentric side? Somebody tell me, what do you see? As we go faster, what happens? That does not look like what happens under concentric scenario. Brenda, what do you see? sorry, so this is faster.
Oh,
So we got to read it as faster, lengthening, faster, short. So as it goes this way, what happens? It plateaus. Does it go down? It goes up a little bit and then it plateaus. But this is significant. When you do an eccentric contraction, as velocity increases, force stays the same. Eccentric contractions are what we call independent of velocity. So if we're going to do our same thing. So in their eccentric conditions, if velocity goes up, but force doesn't change, what does that tell us about what's happening at the cross bridge? We got 3 minutes, I'll wait. Brian,
Could you ask the question one more time?
I'm going faster doing an eccentric contraction. But force is not going down. So what can that tell us? The fact that force isn't going down, what does that tell us about what's happening at the cross bridge as eccentric contractions go faster and faster?
They're not detaching.
They're not detaching. Perfect. When you do an eccentric contraction, the cross bridges don't detach. You're lengthening, not shortening. So cross bridges don't have to detach. So that means I can maintain force, but I'm actually getting more. Where's the extra force coming from? Anybody want to guess? Anybody ever shot a rubber band at your friend or neighbor or enemy or something? Anybody ever done that? No? Brenda's like, no, I would never do that. Of course not. Rule followers. It's okay. Right? If you're going to shoot a rubber band at somebody, what do? You stretch it. Okay? You stretch it, and when you stretch the rubber band, what are you storing as you do that? You guys know? Potential energy, right? Okay. And then you let go, and that potential energy gets used in the rubber band by being elastic, means it wants to go back to its original shape. So you stretch it out, and it wants to go back to being short. And in doing that, it releases that energy and it gets applied. You have something in your muscles or in somewhere in this whole system that's pretty stretchy. Ryan's nodding his head and saying yes. What might those things be? We've talked about them already. What is stretching? Tendons, good. What else? There's something around the fibers that's stretching.
Collagen.
Collagen. What's made up of collagen? What things did we already talk about that are made up of collagen?
Bones.
Bones? Not quite. Tendons, yes. Ligaments, yes, but what else? It's not the fiber itself, but it's something around the fiber. Fascia, right? Connective tissue, right? We talked about the epimysium, the paramysium, the endomysium. They're made up of those things. You've got collagen also in the tendons. So as I stretch, that connective tissue doesn't want to get stretched out. It's like a rubber band. It's resisting against getting stretched. And that adds some force to the entire system. So eccentric contractions are able to generate the most force. You can lower down more weight than you could ever hope to pick up because you get max muscle force or muscle torque because the cross bridges don't cycle, plus you get extra from that stored potential energy and the elasticity in connective tissue and tendons and ligaments. Okay? So if you want to win a bet with your friend, go to the gym today and tell them you can lift more weight than them. And just make sure you lower it down and they're picking it up. Okay? All right. We'll stop here. We'll do the power slide on Wednesday. We'll do sensory motor stuff on Wednesday. Then we'll have Jeopardy on Friday. Okay? All right. Thanks, guys.
Peer reviews are due tonight, so please get those in so you and your group members can get y'all's grades.
yeah.